In the second part of Chapter A, we are going to discuss the quantum mechanics and electronic configuration. In this lecture, we are going to study how we can distribute the electrons in the orbits of an atom. In order to study the electronic configuration, we need to know about the electronic quantum numbers. Quantum mechanics describes the energy states of an electron with 4 quantum numbers. The first one is the principal quantum number, and this describes the electronic orbits in an atom. And each energy level is assigned with one principal quantum number. This number can be 1, 2, 3, 4, 5, etc. The second one is the angular momentum quantum number, that is represented by the letter L. Each principal energy level has specific sublevels or subshells where the probability of finding an electron is high. These quantum numbers are represented by the letter S, B, D, F, G, H, etc. This quantum number also is related to the shape of the orbital. We can see here, if we had S orbital, then we will have like a circle. But if we had P orbital, we will have like A-like shape. The third is the magnetic quantum number, that is represented by the letter M, and this denotes the orientation of the electrons along to the axis. For example, if we had the P orbital, then this corresponds to this orbital along the x-axis, and this is why it's px. Py is the P orbital along the y-axis, and Pz corresponds to the P orbital along the z-axis. And the last one is the spin quantum number, that is represented by the letter S and corresponds to the electronic spin orientation, as if the electron is spin up or is spin down. Then, just to summarize, we had 4 electronic quantum numbers. N corresponds to the principal quantum number, and this is related to the distance from the nucleus. The second one is the L, which is the angular quantum number, and is related to the shape of the orbital. The third one is the magnetic quantum number, and is related to the orientation of the orbital in space. And the second one is the spin quantum number, and is correspond to the electron spin. In this course, we will concentrate in the first 2 quantum numbers to describe how we can organize the electrons in the orbitals. We usually represent the orbits as concentric circles because it's easy to understand in this way. But I want to show what is the real shape of the orbit. In the first graph, we have the orbit S that least corresponds like a sphere, and this orbit can hold 2 electrons. In the second graph, we have the p orbitals, and we can see this orbital has 3 pairs of lobes. Each lobe can hold 2 electrons. Then the total numbers in orbital p will be 6 electrons. And in the last graph, we had the shape for the orbitals, and it's really complex. In this case, we had 6 sets of lobes. Each lobe can hold 2 electrons. Then this is why in the orbitals we had the 10 electrons, maximum 10 electrons. Then, just to summarize, in S orbital holds 2 electrons, p orbital holds 6 electrons, and d orbital holds 10 electrons. In this table, we summarize the quantum numbers and electron distribution of the main energy levels from n equal 1 to n equal 4, and what are the associated subshells with each of these main energy levels. Also, what is the maximum number of electrons in each subshell, and what is the maximum number of electrons for main subshell. And we can see in case of the n equal 1, we have just one subshell. And remember, S holds just 2 electrons, and this is why the maximum number in this subshells is 2, and then the maximum number in the main energy levels will be also 2. And let's see what happened with the second energy level, n equal 2. And in this case, we had 2 subshells. We had S, P. S holds 2 electrons, P 6 electrons. If we add these two, the maximum electrons in the second main energy level will be 8. Let's see what happened with the third energy level. We had 3 subshells, S, P, D. S holds 2 electrons, P 6 electrons, D 10 electrons. If we add these 3 numbers, we will get the maximum electrons in the third energy level will be 18. Let's see the last one. For n equal 4, we had 4 subshells, S, P, D, F. S holds 2 electrons, P 6, D 10, and F 14. If we add together these 4 numbers, we will get 32, which is the maximum number of electrons in the 4th energy level. Now we are going to represent the information of the previous table in a diagram. In this diagram, the blue circle corresponds to the nucleus of the atom, and this circle corresponds to the first energy level. This is why this corresponds to n equals 1. And we know the first energy level has just one subshell. And then this subshell will be 1s. Now we had the second orbital, and the second orbital we know has 2 subshells, S and P. Then this is why this will be n equals 2, and this corresponds to the subshell 2s, and this corresponds to the subshell 2p. This corresponds to the third orbital, means to n equal 3. This shell corresponds to 3s, and because it's the third orbital, we will have 3 subshells. The first corresponds to 3s, the second subshell will be 3p, and the last one will be 3d. And now we had the 4th energy level, and this corresponds to n equal 4, because it's the 4th energy level. This has 4 subshells, and the first subshell corresponds to 4s, the second one corresponds to 4p, the third one corresponds to 4d, and the last one will be 4f. Then this is how we can represent what we discussed in the previous table in this diagram. One more thing that is important to remember is the S subshell can hold maximum 2 electrons. p subshell can hold maximum 6 electrons. D subshells can hold maximum 10 electrons, and F can hold maximum 14 electrons. To write the electronic configuration of an atom, we need to know the number of electrons. We can find this information in the periodic table. For example, in case of carbon, you will find the element name, and the number below of the element name is the atomic number, which corresponds to the number of protons. Then you will find the symbol of the element, which for carbon corresponds to C, and this number corresponds to the atomic mass. In case of the neutral atoms, the number of protons equals to the number of electrons. Then we can conclude, in case of the neutral atoms, the atomic number equals to the number of electrons. Then this number is above the symbol corresponds to the number of electrons. We will study two different ways to determine the electronic configuration of an element. One is the chart, and the other one is the periodic table. To determine the electronic configuration using a chart, we will use a matrix which shows the order in which the orbits are filled. In the matrix, we have the principal quantum numbers and the respective subshell. Remember, S subshell can hold up to 2 electrons. P up to 6 electrons, D up to 10 electrons, and F holds up to 14 electrons. To find the electronic configuration of an element, the first thing we need to know is the number of electrons of the element. To know that, we will use the periodic table. Above the symbol, you will see a number. That number corresponds to the atomic number. And this is telling us the number of protons in the nucleus of the atom. If the atom is neutral, then this number also corresponds to the number of electrons. For example, lithium has 3 electrons, carbon 6 electrons, nickel 28 electrons, barium 56, and etc. Also, we will use this chart to write the electronic configuration of any of these elements. Remember, this chart shows the order in which the orbitals are filled. Always we will start filling from the innermost orbital to the outermost orbital. Also, we need to remember the subshell S holds up to 2 electrons. Subshell P holds up to 6 electrons, D up to 10 electrons, and F up to 14 electrons. With all this information, then let's start writing the electronic configuration for some elements. Let's start with beryllium. And we know beryllium has 4 electrons. Then we will write the electronic configuration, follow the direction of the arrows. Then we will start from here. We will move down 1s, then 1s, and we know S holds up to 2 electrons, then 1s, 2. Then let's move to the next row, will be 2s, And we know S can hold up to 2 electrons. And now we can see if we add 2 plus 2, we had 4. And this is the number of electrons for beryllium. Then this is the electron configuration for beryllium. And let's write one more. If we write, for example, for fluorine, and fluorine has 9 electrons. Then we will follow the same procedure. We will start from the innermost orbital, which is the first row. Then we have 1s, and the subshell S holds 2 electrons, and will be 1 S2. We move to the next. In this direction will be 2 S2. Move to the next. Always from right to left. 2p. P can hold up to 10 electrons, but we need just 9 electrons. Then we had 2 plus 2, 4. Then we need 5 more. Then this here we just write 5. Because if we add the number of electrons we had in each subshell, this must be equal to 9. Then 2 plus 2 is 4, plus 5 is 9. Then this corresponds to the electronic configuration for fluorine. Now let's write for aluminum. And for aluminum, we have 13 electrons. Then we start from right to left, from the innermost orbital, which is 1s, 2, because here we had 2 electrons. Then we had 2s2. Then we had, from here in this direction, we had 2p, 6. And we need 3 more, because we had 2 plus 2 is 4, plus 2 is 10, plus 6 is 10. Then we need 3 more. Then 2p6, 3s2. Now the next, we start from the next row will be 3p. P holds maximum 6 electrons, but we need just 1 more. Then we will write here 1. And if we add all these numbers together, we should get 13. Then 4, 10, 12, 13. Then this is the electronic configuration for aluminum. And now let's write the electronic configuration for calcium. And we will follow the same procedure. And let's write here calcium. And the number of electrons for calcium is 20 electrons. Then let's start. And we will have 1s2. The next, from right to left, 2s2. The next, in this direction, always 2p6. (3s2), and we will fill all these shells, orbitals, until we complete 20 electrons. Then 3s2, then 3p6, (4s2). Then let's see how many electrons we had now. We had 10, 12, 18, 20. Then we had 20 electrons. Then this corresponds to the electronic configuration for calcium. Then let's write for iron. Then iron Let me write this one up. For iron, we had 26 electrons. Then let's write now 1s2, 2s2, next 2p6, next 3s2, next 3p6, next 4s2, and let's count. We know up to this shell we had 20 electrons because it's the same configuration for calcium. We had 20 electrons, and we need six more electrons. Then now we will move to the next. Then will be 3d, but d holds maximum 14 electrons, but we need six more electrons only. Then we will write just here 6, and this corresponds to the electronic configuration for iron. Now let's write for barium. Barium has 56 electrons, and we have here barium 56 electrons. And then let's start from here. Yes, from the innermost orbital. Then will be 1s2, because this orbital maximum holds 2 electrons. Then 1s2. Next 2s2. Then will be 2p6. The next will be 3s2. Next will be 3p6. Next 4s2. Then we have 3d. Let me write here 3d10. 4p6. 4p6, 5s2, and now next 4d10, 5p6, and 6s2. And we can add these numbers together, and we should get 56 electrons. Then we had 10 plus 10, we had 20, 30, 36, 38, 48, 54, 56. Then now we know we had the electronic configuration for barium. Now we are going to study the second way we can find the electronic configuration of an element, and this way is using the periodic table. We are going to see the correlation between orbitals, suborbitals, and the periodic table. This way is important because you will understand the location of the elements in the periodic table is telling us, for example, if the material is metal, is non-metal, or how many electrons that element has in the last shell. And this information is important when we are studying ionic compounds or chemical reactions, for example. The rows of the periodic table are associated with the principal quantum number of the orbitals. For example, we can see the n equal 1 corresponds to the first row, the n equals 2 corresponds to the second row, the n equals 3 corresponds to the third row, 4, 5, 6, 7 each correspond to the respective row. Also, the periodic table is divided by blocks. each block is associated with a subshell. And this is why we can see here this block is S block, this is P block, this is D block, and this is F block. Now let's see what happened with the orbitals. In case of the S and P block, the row corresponds with the orbital. For example, the first row corresponds with the first orbital. The third row corresponds with the third orbital. But this is not the case of the group D and F. In case of the group D, the row number 4 doesn't correspond to the orbital 4. We can see 1, 2, 3, 4. And in this case, for group D, will be 4 minus 1. Then the fourth row corresponds to the third orbital D. The row number 5 corresponds to the orbital 4 because it's 5 minus 1. Then in case of the D, the orbital will be 3, 4, 5, 6. Now, in case of the group F, F is related, or this group is related to the row 6 and 7 in the periodic table. And we will see later why it's like that. And in case of the group F, this is not the orbital 6, will be 6 minus 2, then will be 4. This is not the orbital number 7, will be 7 minus 2, which is 5. Then here we have, in case of the F block, this orbital will be 4 and this orbital will be 5. Another thing you can see that helium corresponds to the S block. However, the location of the helium is in the P block. The reason is, even though helium corresponds to the S block, the properties of the helium are similar to the properties of the elements in this column of the periodic table. This corresponds to the noble gases. And this is why helium is located in the periodic table in this column, but helium belongs to the S block. Let's talk about each block a little more in detail. Then we know the subshell S holds up to 2 electrons. Then this is why the block S has 1, 2 columns, because the S shell can hold up to 2 electrons. We know the shell P holds up to 6 electrons, and this is why the number of columns in the P block are 6. Then we can see here is 1, 2, 3, 4, 5, and here we have number 6. Also, in case of the D shell, it can hold up to 10 electrons. And this is why the D block has 10 columns. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And also the shell F holds up to 14 electrons. And this is why we had 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. Using this information, we are able to know what is the outermost shell for any of these elements of the S block or the P block. in the case of the D and F block, we have to be more careful. For example, if we want to know what is the outermost shell, for example, for lithium, then lithium is in the second row will be 2, is in the S group will be 2S, and because it's in the first column will be 2S1. For calcium, what is the outermost shell in case of calcium? Then it's in the fourth row, then will be 4, it's in the S group will be 4S, and it's in the second column will be 4S2. Then let's see in case of the barium. In case of the barium will be 6S2. 6S2. Then let's see one example in the group P. For carbon. Carbon will be first the orbital, the main orbital will be 2. Then P, because it's in the P block, 2P, and it's in the second column will be 2P2. We are talking about just the outermost shell. In case of the aluminum, then will be, is in the third row, yes, will be 3P1, will be 3P1. Let's see what happened with chlorine. Then it's in the third row will be 3P, and it's 1, 2, 3, 4, 5. Then will be 3P5. This is the outermost shell for chlorine. Let's do one more example for krypton. For krypton will be 4P6. And the outermost shell in case of krypton will be 4P6. And we will know what is the outermost shell in case of the S and P group just if we have the periodic table. Now we are going to learn how we can write the complete electronic configuration using the periodic table. Then let's start with hydrogen. We know hydrogen has 1 electron. And because hydrogen is in the first row, then we have 1 is in the S group, S, and is in the first column, then is 1s1. And this is the electronic configuration for hydrogen. Let's try to represent this one in a diagram. Then we had here the nucleus of the hydrogen. And we know this corresponds to the shell, to the orbital n equal 1, and this has just 1 suborbital. And here the s orbital or suborbital holds up to 2 electrons. Then let's write here maximum 2 electrons. Then we had 1, then it's okay. Then now we had the electronic configuration in case of the hydrogen is 1s1, and this is how we can represent this one using a diagram. Yes, this is the first orbital, has 1 suborbital, and this is the electron. Then let's now try helium. And we know helium has 2 electrons. And remember, helium is here, but because the properties of all these gases are similar, but the real position of helium should be here. And this is why it's blue also. Then helium belongs to the S group. then it's in the first row, S is in the first row, S block, and it's in the second column, 1, 2. This is why we will write here 2. And this is the electronic configuration of the helium. Then now let's try to write this one in. This is the nucleus of the helium. N equal 1 is the first orbital, and this is the subshell or suborbital S, and then we had 1, 2 electrons. Remember, S holds up to 2 electrons. And this is how we can represent the diagram, and this is how we can write the electronic configuration of the helium. Now let's try beryllium. Beryllium, 4 electrons. Yes, this is the atomic number. The atomic number is telling us how many electrons. In case of the neutral atoms, then we had 4 electrons. Then let's see. If the beryllium is in the second row, it's because the other shells, the other orbitals are completed, are full. Then this is why we always will start from the innermost orbital. Means we will start from here. And then we will move from here, then here. Then we know if the beryllium is here, it's because this orbital is completed, it's full. Then we need to start always from here. Then we start here, then this orbital is completed, means is 1, S, 2. Remember, S holds up to 2 electrons. Then 1 is 2. And this 2, I will write this time like that. These are completed. Then we need to now write for this 2. And 1 is 2. Now 2 is, because it's in the second column, is 2. And this is the electronic configuration in case of beryllium. How we can represent this? Then we had here. Now we need to write this one smaller. And this corresponds to N equals 1 S 2. Because S holds up to 2 electrons, we cannot put more electrons in this shell. Then now we need to move to the next. And this corresponds to N equals 2, and this corresponds to 2S. Maybe I should write here 1S. This way we don't get confused. This 1S. Let me write here also 1S. This is 2S. And 2S holds up to 2 electrons. Then this will be the diagram in case of the beryllium. Now let's try oxygen. And how many electrons for oxygen? 8. Remember, if the position of the element is here, it's because the other shells are completed. And we will start always from the innermost shell. Will be for 1 S 2, and we need to complete this 2. Will be 1 S 2. Then we need to move to the next. Will be 2 S 2, 2 S. This is the block S 2 S 2. Now we need to move to the group P. Then will be 2P. This is 2P. And let's see 1, 2, 3, 4. Then 2p, 4. And we will had 8 electrons as we expected, because we had 8 electrons for oxygen. Then let's now write the diagram. Let me write a little smaller this. And this is the nucleus. Here we had for 1s. We'll write like that. I don't have too much space. Then we had 2. Let me write here 2s, and here s holds up to 2 electrons, and then we had to write 2p. Yes, this is another subshell for the second orbital. And in this case we had 4. Remember, p holds up to 6 electrons. And here we had 4. And 1, 2, 3, 4. We have 2 for n equal 1, and we had 6 for n equal 2. Remember, these two subshells S and P belong to the second orbital. Let's try the last example. Let's try for neon. And in case of neon, we had 10 electrons. Then we had here neon. And this is we had 10 electrons. Let's now, if the neon is here, is the shells, the other shells, or the shells before this one must be completed. And always we will start from the innermost shell, which is 1s, in this case 1s2. As these two are completed, then 1s2, then 2s2 also is completed, and then 2p, one, 2, 3, 4, 5, 6. And now we have the electronic configuration for neon, which is 1s2, 2s2, and 2p6. Let me write this one better. 2p6. Now let's represent this one in a diagram. Then here is the nucleus. This corresponds to the orbital 1s2, which is this one. This is the first one, is this one. And this corresponds to n equals 1. Now we are going to represent the second orbital, which has those two suborbitals, S and P. And this corresponds to 2s. Let's write this one. Yeah, this corresponds to 2s. And this can hold up to 2 electrons. And then we had 2p, can hold up to 6 electrons. This is the max. This 1, 2, 3, 4, 5, 6. These two subshells belong to the orbital n equal 2. This is why we have 2s, 2p. Now let's try titanium, and we will write titanium here in one side. And for titanium, we had 22 electrons. And we will follow the same procedure. And we had 1s2. Then we had here 2s2. 2p6, 3s2, 3p6, 4s2, and when we are in the group D, we had to be careful because in this case it's not 4d2. In this case, we had to take into account this rule. This is 4 minus 1 will be 3. Will be 3d1, 2 because it's in the second column of the D block. Then it's 1, 2. And will be 4 minus 1 will be 3d1, 2. Then 3d2. So we can write this one here. 3d2. If we add the electrons together, we should get 22. And we had 10 here up to here. Another 10 will be 20 plus 2, 22. Then we had 22 electrons here. Then this is the electronic configuration for titanium. Now let's do the electronic configuration for arsenic. Then arsenic, the number of electrons for arsenic is 33. And let's type arsenic electrons. Let's do the same procedure. And we have 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, 4 is 2. This is completed. Maximum electrons in D shell is 10 electrons. Then, and it's not 4. As we now we know it's 4 minus 1 will be 3 D 10. And we can count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10. Now, this is P group, then it's 4. Yes, because P is N. Then it's 4P. Now we count 1, 2, 3, 4P, 3. And this is the electronic configuration for arsenic. If you add this together, you should get 33. Yes, we had up to here we had 10, another 10, we had 20, 30, 33. And this is the electronic configuration in case of the arsenic. Let's try now bromine. And how many electrons in case of bromine? We had 35 electrons. Yes, it's just here. Let's see. And just now let's do the same procedure. 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, 4 is 2, It's not 4, it's 3. 3, D10. Now here we have 4P. 4P, 1, 2, 3, 4, 5. It's 4P5. And let's try now krypton. And how many electrons for krypton? 36. And yes, now do the same thing. Yes, follow the same procedure. The 1 is 2. 2 is 2. 2p6. 3 is 2. 3p6. 4 is 2. We know it's 3d10. Now here we had 4p and it's completed. Yes, 1, 2, 3, 4, 5, 6. And it's 4p6. And now we should get 36 electrons if we add these numbers together. It's 10 plus 10 is 20 plus 10 is 30, 36. This is the number of electrons in case of krypton. One more thing I want we check in these results is what is the number of electrons in the outermost shells in each case. And in case of the magnesium, because this is the third shell, we had 2 electrons. Yes. In case of the calcium, the outermost shells is the 4, or the outermost orbit is the 4, is the number 4. Then we had 2 electrons. Yes. In both cases, for magnesium and calcium, the outermost shell has 2 electrons. Yes. We are talking about this number. And we know this is the outermost because this is 1, this is the second orbit, this is the third orbit. This is the first orbit, the second, the third, this is the fourth orbit. This is the outermost orbit. The magnesium and calcium, they had 2 electrons in the outermost shell. Let's see where is magnesium. Magnesium is here, calcium is here. Now we are going to learn how to write the condensed or the abbreviated electronic configuration. To write the condensed or electronic configuration, we will use the noble gases electronic configuration, or we will base it on the noble gases electronic configuration. Let's write one example to understand how we can do that. And let's write the electronic configuration for xenon. Then xenon we had 54 electrons. And let's write, then we know is this position, the other orbits are completed, then we will start here 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, 4 is 2. In this case is no, 4 is 3, and 3d10. Now again 4p6, 5 is 2. It's not 5, it's 4d10. Now we had in this case again 5p6, 6 because it's completed. Yes, 5p6. Then let's write now the electronic configuration in case of barium. In case of barium, we had 56 electrons. Is right here. And let's now write for barium. And we will follow the same procedure. We had 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, it's not 4, it's 3d10, again 4p6, 5s2, 4d10, remember it's not 5, it's 5 minus 1, it's 4d10. Now this is completed also, then we'll 5p6, and then finally we had 6s2. And what we can notice if we compare these two electronic configurations is they are almost the same. Yes, the first part of the barium configuration corresponds to the xenon configuration. Then we can write, instead of repeat all this, we can write the electronic configuration for barium like xenon using the brackets that indicate this corresponds to xenon, and just we will add this part. This is how we can write the electronic configuration in condensed way. Now let's see how do we write an electronic configuration for cerium. And let's see why we want to write the electronic configuration for this element. And lanthanum is here, but cerium is here. Well, you can see lanthanum is 57, but after lanthanum we had hafnium, and hafnium is not 58, it's 72. Then the 58 is cerium. And these elements are in this group because they had similar properties. But according to the atomic number, the position of this element must be here. Yes, must be here after lanthanum. Then in this case, we had to be careful when we write the last part of the electronic configuration of cerium. In the first part, we will just write in the way we already know, but when we reach to this part, then you see we need to move from here to here. And let's write here this information. We had lanthanum 57, we had lanthanum here, and right here we had 58, and this corresponds to cerium. And now let's write the electronic configuration up to here, and let's see what happened after that. Then we want to write the electronic configuration for cerium, which has 78 electrons. Then we start, we know 1s2, then 2s2, then 2p6, 3s2, 3p6, 4s2. Here we know it's not 4, it's 3, 3p10, 4p6, 5s2, is 4D10, 5P6, 6S2. Then now we need to here stop a little bit, and we need to write 57. Then 57 is in 5. What position is 57? It's 5D1. Yes, 5D, but it's in the first. Then it's here is 5. Then we will write that 5D1. Now we need to move down, because here we had 57, 58, and in 58 we had 4F. Remember, here is no 6, is 4. 6 minus 2 is 4, is 4F, and because it's in the first position, then it's 4F1. And this is the electronic configuration for Sirion. Now, how do we write an electronic configuration in case of half-mune? And let's see what we are interested in half-mune. And half-mune is here, and it is 72. Then we had 57 for lantern on here. We had half-mune, 72. And we already discussed, we had here Sirion, and here is 71. Then we can see in this case the first part of the electronic configuration is the same as we are doing before. Yes, we will write the same way. But when we reach to this point, we need to be careful. Yes, because in this case we can see we had to move down because it's 58. We need to pass through all this group, and then we need to come back. And let's write the first part of the electronic configuration for half-mune, and then we will take care of the last part. We will just explain in detail how we can do that part. Then for half-mune, we had 72 electrons. And let's write the electronic configuration for half-mune, and we will do the same we are doing before. This is 1s2, 2s2, 2p6, 3s2, 3p6. All these shells are completed. And this is 4 and 3d10, then 4p6, 5s2, 4d10, 5p6, 6s2. And we can see half-mune is in the group D. But first we need to move to the group F, and we need to come back to the group D. Because we will come back to the group D, we will take care of the group D at the end. And now we are right here. Then we will move down. Yes, from here to here we will move down. And then now we have the group F. And we can see the group F is completed. Yes, we need to pass through all group F. And now we have 4F, 14. And now we complete this one, we move through all this, and now we need to come back to the group D. Now group D in this case will be 5D, And let's see in what position is hafnium. It's in the second column of the D block. 1, 2. Then this is why we will write here 2 electrons. And this is the electron configuration in case of the hafnium. Just when you had to write the electron configuration for the elements with the atomic number greater than 57, just you need to be careful with this part. Yes, you have to be careful is that the 57 we need to move to this group as first. And this is the only thing we need to be careful in that case. Up to now we had discussed the electronic configuration of the neutral atom, like we had in this example. And this is a lithium neutral atom, and we had 3 protons and 3 electrons. Then this is why we say this is a neutral atom, has the same number of positive and negative charges. An ion is an element that had gain or lose electrons. For example, if the atom had more electrons than protons, like in this example, then we say this atom is negatively charged. If the atom has more electrons than protons, like in this example, then we say this atom is positively charged. In order to write the electronic configuration of the ions, we need to follow 2 steps. The step number 1 is to find the electronic configuration of the corresponding neutral atom, and the second is the electrons that are going to be lost or gained should be from the outermost shell. Let's write the electron configuration for some ions. Let's start with the negatively charged ion, sulfur -2. This -2 means sulfur gained 2 electrons. And according to the step number 1, we need to find the electronic configuration of the neutral atom. In this case, will be sulfur. Then let's see how many electrons in case of sulfur. Sulfur is right here. Then we had, in this case, sulfur has 16 electrons. Let's write the electronic configuration in case of sulfur. Let's write first the electronic configuration in case of sulfur. Then we had 1 is 2, 2 is 2, will be 2, 6, the next will be 3 is 2, and 3p 1, 2, 3, 4, then 3p 4. But now, because we want to write the electronic configuration for sulfur -2, we need to add 2 electrons to the outermost shell. In this case, the outermost shell is 3p4. Then the configuration for the ion will be 1s2, 2s2, 2p6, 3s2, 3p, 4 plus 2 is 6. And we can see in this case, sulfur -2 has 18 electrons. Yes, 2 more than sulfur. And we have 2, 4, 10, 12, 18 electrons. In this example, we want to write the electronic configuration of the mercury +1. And the first thing we want to do is to write the electronic configuration of the neutral atom, in this case the mercury atom. And mercury is, in the periodic table, is the atomic number is 80, then mercury has 80 electrons. In order just to simplify the electronic configuration, let's write in abbreviated way. Then we will use the noble gases notation, and then the nearest noble gases is xenon. Then let's start from here. Then we can write
the abbreviated electronic configuration. We start from xenon, then we will move to the next, will be 6s2. Remember, in this case, we need to move to the group F because it's 56, 50, and then we will go back to group D. Then 56, we move through all group F, and we did this part. Now all this part then will be, and it's not 6, it's 6 minus 2 will be 6 minus 2 is 4, F14. Now we go back to the group D, then D in this case is now 6, 6 minus 1 is 5, and will be 5D10. Now we are ready to write the electronic configuration for mercury plus 1. And remember, in this case, the outermost shell is 6s. Then we need to, in this case, we will need to remove one electron from this shell. Then let's rewrite and let's organize the two shells, 4 in order D, and will be 6s, but it's not S2 because it's lose one electron. Then will be, this will be the electronic configuration in case of the mercury plus 1. And in this case, for mercury neutral, we had 80 electrons. For mercury plus 1, we will have 79.
The last concept we want to discuss today is the isoelectric. When the ions or atoms, they have the same number of electrons, we say they are isoelectric. If they have the same number of electrons, means they have the same electronic configuration. Then now we have here two ions of chlorine. Then the first ion corresponds to the chlorine's -1. If it's -1, means the chlorine gain one electron. Yes. If the chlorine is +1, means the chlorine lose one electron. Then let's see how many electrons in case of the neutral chlorine. If the chlorine is neutral, then it has 17 electrons. But if chlorine gain one electron, because in this case it's -1, gain one electron, then the number of electrons in this, for these ions, will be 17 plus 1, maybe, then will be 18 electrons. And let's see what happened with the second ion. The second ion is chlorine plus 1, means chlorine lose one electron. If it lose one electron, then will be the number of electrons for this ion will be 17 minus 1, and will be 16. Let's write here 16 electrons. And because the number of electrons are not the same, we will say they are not isoelectric. And let's see the second problem. We have bromine -1, means bromine gain 1 electron. Let's see what is pure bromine is. The neutral bromine is 35. And because gain 1 electron, then this ion of bromine will be had 36. This 35 plus 1 will be 36 electrons. Because bromine gain 1 electron, is negatively charged. Then What happened with krypton? There is no any number here. If there is no any number means we had neutral atom. Then krypton is 36 electrons. And because bromine -1 has 36 electrons and krypton has also 36 electrons, they have the same number of electrons. Then we say, yes, they are isoelectric.